it. Next week is test week. All right, binomial distribution we're going to talk about. Okay, so a binomial experiment, this is not on your paper. If you just want to like put a couple notes in the margin maybe about what makes it a binomial experiment. So binomial experiments are specific instances of those probability distributions that we were looking at before. So it consists of n identical trials. Okay, so when we perform an experiment, every trial is exactly the same, and n of them are what we're doing. Each trial will only have two outcomes. So there's only like one thing that we're looking for, and we either have success or failure in that one thing that we are looking for. Okay. The probabilities will remain constant from trial to trial, again, because they are identical trials. The probability of a single trial is P, what we're going to use. The probability of failure is the complement of P, everything else. Okay, again, because there's only two outcomes, success or failure. Trials are independent of one another. Okay, so one does not depend on the other. And then X is the number of successes that we then analyze in any given experiment. Okay, so N trials, two outcomes, which are success or failure. P is our probability of success. Q is our probability of failure. Trials are independent of one another, and X is the number of successes. Okay. Good. All right. So I think this is the first one I've got on your slides there. So it says, determine whether each of these experiments is a binomial experiment. If it is, specify the values of N, P, and Q, and then list the possible values of X. If it is not, explain why. Okay, so the first one is, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. Okay, so we first want to make sure it meets the conditions of a binomial experiment. Do we have two outcomes, success or failure? Yes. Are the outcomes or the trials or the surgeries independent of one another? Yes. Okay, so those are the big things that we look for. So this is a binomial experiment. And then we should be able to then name all of these variables. So N is the number of trials that are being completed. So number of surgeries that are being completed. In this example, it is 8. Okay. P is the probability of success of any one trial. So in this case, 0.85 or 85%. Q is the probability of failure of any one trial, which is the complement of our success probability, 1 minus 0.85. So 0.15. And then X will assume a lot of possible values. This is kind of like those tables we were doing before in the last section. It's all the possible successes that could happen. So because my N is 8, here my X is every number 0. I could have 0 successes potentially. Probability is probably pretty low, all the way up to 8. Are the possible number of successes that could happen in that situation. Okay. One below it, a jar contains 5 red marbles, 9 blue marbles, 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Okay, so is this a success, failure, 2 outcome situation? Yes, if my random variable represents the number of red marbles. When I draw a marble out, it's either red or it's not red. Okay, success or failure. So even though there's other colors in there, I still have 2 outcomes. The problem here is this. It says without replacement. So if I don't replace something, doesn't that change the probability on the next trial? So it's a dependent situation, and it has to be independent trials to be a binomial experiment. So this is not, bless you, not binomial because they are not replacing, because the probabilities change, because the trials are not independent of one another. Okay. questions on recognizing a binomial experiment? Finding our variables. Okay, moving on. All right, so formula for calculating binomial probability is this guy here. This is really the one that we're going to be using. Now, they've written it out like in full with all the factorial symbols to recognize the combination there. If you remember the formula we did with combinations a couple sections ago, that's what you see first on the right here. But pretty much if I have a binomial experiment and I want to count the probability of a certain X number of successes, so maybe we're back to that surgery example, and I want to calculate how many, what's the probability of having 5 successful surgeries? Exactly, 5 successful surgeries. That's where this would come in handy. It's kind of hard to calculate by hand because there's a lot of different ways that I could have 5 successful surgeries and failures, and we have to account for all of those. And that's what that combination part of the formula does for us. So let's say I did that. I wanted to find the probability in that last example of 5 successful surgeries, okay? There were 8 possible surgeries that were happening. That was my N. Choose 5. So that's all the way that 5 could be successful. And then we want to also include in the probabilities. My p-value in that example was 0.85, the probability of success. And when we take it to the number of successes we're looking for, x value, so 5 successful surgeries. Then we take our Q, our complement, our probability of failure, 0.15, and take it to the power of the number of failure surgeries we had. And those two numbers add to n, which is what that x and n minus x in the exponent tell us. Okay, so probability of success to the power of the number of successes, probability of failure to the power of the number of failures. And then out front, all the different ways that we can combine those together. And then you would type this in the calculator, and that would be the probability of exactly 5 successful surgeries. Okay, so example at the bottom, there's a 40% chance of rain for the next 3 days. What is the probability that it will rain on exactly 1 day? So it is helpful to name all those variables first. What is n in this problem? The number of trials, or the number of days that we're analyzing. What's my n? 3. And then what are my possible values of x in this problem? 1, 2, 3, or 0. Could rain 0 days. P, probability of success, which is considered rain in this case, 0.4. And then Q, probability of failure, so no rain, 0.6. Okay, so if I'm using my binomial formula at the top, the probability that it will rain on exactly 1 day looks like 3 choose 1 times my probability of success, 0.4 to the power of 1, because we want it to rain on 1 day, and then 0.6 to the power of 2, we want it to not rain on 2 days. And then type it in your calculator. So 3 choose 1, actually I just know that one, that's going to be 3, times 0.4 times 0.6 squared. And I get 0.432. So if I want to calculate the probability of rain for 1 day, it's 0.6 times 0.6 times 0.4, but the 0.4 could go 3 different places. It could be on the first day, the second day, or the third day. So that's why we end up multiplying by 3, that combination that does that for us. Any questions? Okay. You obviously don't need to write this down. This is the work that you would have to do if you do not use the binomial theorem that we just talked about, that formula. And this is only for 3 different trials. Imagine how big this chart would be if I was looking at like 8 days or 10 days in a row. So the formula definitely saves us a lot of time, but you can kind of see days of rain. There's 3 different places where that's happening. I kind of mentioned that a second ago. It can rain on the 3rd day, the 2nd day, or the 1st day. And if you take all of those probabilities and multiply them together, they each end up being 0.144, and then you add all of those up and you end up with 0.432. So it's doing all that work for us all at once, which is really nice. All right, so let's look at this one now. I think this one's on your paper. This one on your paper? Yeah, okay. Survey found that 70% of the US adults say that the Google News is a major source of news for them. You randomly select 4 adults and ask them whether Google News is a major source of news for them. What is the probability that exactly 2 of them respond yes, at least 2 of them respond yes, and fewer than 2 of them respond yes? Okay, so it's either a yes or no situation. It's binomial. We're asking people independently. It's independent, so we have a binomial experiment. What's N? N is 4, people being asked. P, probability of success. So probability that they're going to say yes in this case. What is it? 0.17. Q, probability that we have failure, that they're going to say no. 0.83. And then X could be all the numbers from 0 to 4. We don't need to list that right now. Okay, first calculation. Find the probability that exactly 2 of them will respond yes. Okay, can somebody set it up for me? What's it going to look like? We just don't want to talk because it's first period. 4 choose. How many am I choosing? 2. And then if I take 0.17, what power is it going to go to? 2. And if I have 0.83, what power is it going to go to? Also 2. Type it in your calculator. Okay. 4, choose 2. 0.17 squared, 0.83 squared, 0.119, if I give it 3 decimal places. Okay. If we change it now and say at least 2 of them respond yes. So at least 2 could be 2 or 3 or 4. And when we use the word or, what are we doing with probabilities? Adding them. So you're going to do this 3 times. And we already have one of them. That one's done for us, 0.119. Okay, but you're going to find the probability that it's exactly 3 people, the probability that it's exactly 4 people, and then we're going to add all of those up. And that's the probability that at least 2 will respond yes. And then I'll let you guys try the last one on your own. Okay, I'll give you a minute. Okay, there we go. So I put the work on there for B. For C, you can do the probability of 0 plus the probability of 1, but fewer than 2 is the complement of at least 2. It's everything else. And I already calculated at least 2, so the short version of that last problem is just do 1 minus your answer to part B. Oh wait, something's wrong on that last one. Hold on. But B, it's not 0.003, I don't think. It's smaller than that, isn't it? Ooh, it is smaller than that. 0.0008. I think I hit something wrong on my calculator. Is that better? Yes. Okay, so 0.001. If I was going to round to 3 decimal places. Thought that was too big. 0.136. There we go. 136. 0.864. I must have copy and pasted the 3 in from the previous one when I typed it in. Okay. Questions on that? Okay. The last slide on the front of your page then, which is the lesson we're going to do together, is how you can take a binomial distribution and find mean, variance, and standard deviation. The great news is you do not need any tables to do any of these. These are really fast formulas. The mean is just your n value times your p. That's it. The variance is n times p times q. That's it. And then the standard deviation, as always, is just the square root of our variance. Okay, so we're going to do that on this example. A card is selected from a standard deck and replaced. The experiment is repeated a total of 5 times. Find the probability of selecting exactly 3 clubs. Find the mean, variance, standard deviation, interpret the results, determine any unusual values. Okay, so what's n in this problem? How many trials do I have? How many? 5? Yep. P, probability of success. So here we're looking at selecting a club. So what's the probability of selecting a club? How many suits are there? 52. 4 suits. 13 over 52, or 1 out of 4, or 0.25. Q, probability of failure. Everybody else? 0.75. I like decimals here. You can, of course, keep the fractions if you want to. Okay, so find the mean, variance, and standard deviation is what we're doing. So starting with the mean, it's just n, 5, times p, 0.25, 1.25. What does that mean? On average, when we perform this experiment, and it's being performed 5 times, 1.25, or between 1 and 2, you might see that on Math Excel, clubs are selected. Okay. So usually about 1 is probably what we would say on that one. We had to pick one number. All right, variance. It's just one step further from our mean. N times P times Q, 0.75. So multiply by 0.75, I get 0.102. We do not interpret that one. Okay. Standard deviation, just the square root of my variance, which was all this stuff. So 0.319 is my standard deviation. Okay. So this would tell me most times 1.25 plus and minus, how do I want to say this? Usually within 2 standard deviations as usual. So we're going to say plus and minus 2 times 0.319 clubs are selected. I'm going to make that a little nicer. Okay. So I'm taking my mean, I'm adding and subtracting on 2 standard deviations because that's my normal amount of data. If I take 1.25 and I add on 2 times my standard deviation, I get 1.888. And if I subtract my standard deviation, 2 of them, I get 0.612. Okay, so somewhere between 0.612 and 1.888. So on average, if this is repeated 5 times, between 0 and 2 clubs are what is expected to happen. And then any unusual values is the last question. So it would be unusual in this case to select 3 clubs because on average between about 0.6 and 1.8 clubs are selected. So anything outside of that range, which I'm just going to use a nice pretty whole number 3, would be then considered unusual. And you could test that if you wanted to. You could find with the binomial theorem the probability of selecting 3 clubs, and you're going to see that it's less than 5%. Remember, that was another way we could test for unusual values. Okay. All right. On the back of your paper, this is an exit ticket, but I don't want to collect it because I want you to have your notes this weekend. So I'm going to make a quick little assignment in Polaris that you're going to take a picture of that and you're going to upload it for me. Okay, and you can probably finish it now. If not, just finish it sometime before midnight tonight. That's it. Okay, just upload that quick little exit ticket. And that is it for our lesson today. I'll do cell phone lotto. You guys can work on that. Let me know if you have questions, and then upload a picture on Polaris when you're done. Good.